Hi everyone, welcome to this webinar about microservice design patterns for data and how GoldenGate can be used to improve, simplify, and put you on a path to next-gen data mesh. My name is Jeff Pollack and I'll be your speaker and host today. Please note we do have Oracle moderators in the Zoom chat, so please feel free to post your questions there. Our team will do our best to answer your questions right now, and any that we can't get to during this webinar will immediately contact you later. This presentation follows Oracle policies for Safe Harbor. We may be discussing futures today, and there's no specific guarantee to deliver on any roadmap items that we may cover. For our agenda, we will begin by discussing background on microservice design patterns for data and some of the challenges that the community has specifically had around working with data in complex and large systems. Next, we'll examine how the intersection of data management and microservices is coming together in a kind of data mesh. In section 3, we will deep dive into 5 key microservice design patterns for data, and we'll take a look at how we could improve and simplify those patterns with change data capture software like Oracle GoldenGate. Finally, we'll wrap up with a quick look at how event processing and streaming fits into the discussion around data mesh and microservices. So let's go ahead and jump on in. Much of today's discussion will focus on challenges and improvement opportunities for working with data assets in microservice design patterns. But let's be totally clear up front that microservices innovations are undoubtedly a great thing for the software industry. After decades of work around object-oriented patterns, service-oriented architecture, and many other frameworks and patterns for software development, we finally hit on some design heuristics that can truly enable mass automation of software components in a truly distributed architecture. Microservice improvements help with DevOps, speeding up development and improving the maintainability of systems. Right now, the revolution happening with service mesh and the frameworks like Nginx, OpenShift, and Istio are just getting started, and there will be previously unimaginable improvements to multi-cloud app deployments that lie ahead in the next few years. However, all that good news doesn't mean that microservices are perfect. In fact, working with data has historically been one of the most cumbersome and problematic areas of microservice deployments. Pundits and advocates of microservices have sometimes adopted rigid and dogmatic ways of looking at the design patterns around data. For example, the dogma that each individual microservice must fully encapsulate its own database has caused ripple effects across the ocean of IT systems and has occasionally resulted in a tsunami of data consistency problems for others. Strict adherence to the dogma means that larger applications must be written from the app tier to accept eventual consistency for data transactions. This can obviously cause problems for important business applications or systems where you want to be certain that the state of the data is good when you save it. And further, any sort of transaction complexity requires that microservice developers tightly coordinate their transaction logic across services, which mostly defeats the principal goal of decoupling in the first place. In order to get around this challenge of tight coupling, the microservice data-driven design community has advocated use of what are called bounded contexts for helping developers who must create microservices that coexist within a common subdomain. Within the scope of the bounded context, some tighter coupling of data objects, also known as aggregates, transaction semantics and event semantics may be assumed to be mutually understood among the services within a given subdomain. You can imagine how difficult this must be, and there's much written about how to exactly agree upon what the boundaries of a subdomain should be. In my own 20 years of experience with semantic data modeling and object-oriented systems, I can say for certain that getting a group of developers to agree on a domain model with a repeatable and consistent precision just isn't very realistic at scale. The real world of big enterprise software systems, data models, and complex business processes that span many layers of organizations is extremely multifaceted. There's a lot of good work out there that already points out the obvious. Data is hard. Data is actually very hard. Microservices innovations thus far have been mainly in the app tiers, but the design patterns for working with data mostly just focus on reducing the role of data tier technology in the architectures. In some ways, the dogma is just overly simplistic by assuming that databases are bad, therefore hide them behind all those layers of microservice APIs. When you put that concept to its logical conclusion, you wind up having to accept a worse architecture for data management, and you also shift all of the complexities of managing transactions, events, and data consistency semantics to whatever code your developers create in the microservices tiers. Speaking as a technologist who began my own career in the app layer of software development, but now focusing more on the data layer in software development, I humbly suggest that we would all be wise to consider the data management software like databases, data lakes, data integration, data science, and analytics have an important and first-class role to play in the architecture. Rather than attempting to push data management into the app tiers with microservice design patterns, let's consider how we can take microservice design principles and apply them into the data management tiers themselves. Data is unquestionably the key asset that companies prize most when investing in digital transformation initiatives. We can't diminish the value of data down to something that is encapsulated and hidden behind layers of microservice APIs. If the applications are the true systems of record for business process, then the event logs are what tells us the complete narrative of the truth. What I mean by the narrative of the truth is that the event log captures all the low-level business and system events with an immutable, time-ordered logbook of what's happened. In contrast, our data stores are a source for the state of the truth, because it is the data management systems that provide us with the data consistency and the durable storage from which our archives and recovery points come from in cases of application failure or log corruption. Once we shift our mindsets to think about microservices, eventing, and data management as all equal and first-class members of the systems architecture, we can focus on using the best tools for the right jobs. Together, when we take the innovative app tier patterns from microservices and we apply them to data and events, we can envision a kind of data mesh. A data mesh should preserve the best benefits of microservices, such as speed of development and improved DevOps for continuous integration, continuous delivery, but it should also empower organizations to apply data management patterns for working with raw data events, curating prepared data, and providing canonical master data entities to anyone in the organization who needs them. The next section of this presentation will explore this idea of a data mesh in a bit more depth. So what exactly is a data mesh? First off, it will be good to acknowledge that many in the industry are talking about data mesh and data fabric concepts, so there really is not a single definition that everybody agrees on. For the purpose of this discussion and to articulate what we feel is critically important, a data mesh is the intersection of key microservices patterns, log-based integration techniques, and polyglot data movement technologies. Microservice patterns are key because they bring the concepts behind modeling, sidecar patterns for distributed administration and DevOps activities. Microservices concepts also include event streaming, which of course is arm in arm with immutable log-based messaging platforms such as Apache Kafka and Apache Pulsar. The foundation of polyglot data movement lies with data replication technologies, which may be used for real-time relational or document-based data movement. Polyglot persistence is provided by converged data stores such as the Oracle database or singleton databases per format. Last but not least, there is a revolution happening around edge and 5G networks that will usher in a future where low latency, high-speed networks are ubiquitous. Taken all together, these patterns and technologies are going to usher in a new kind of architecture that can integrate and govern enterprise data assets across distributed and multi-cloud environments. We believe that the market is going through a fundamental transformation away from classical data management architectures like Inman, Kimball, Lambda, and Kappa. These legacy architectures are like monolithic mainframes. They got the job done, but were too centralized, too brittle, and too expensive. The big Lambda and Kappa architectures got us into polyglot data and elevated the status of the speed layer, but they have rapidly become known for being brittle and overcomplicated. Even the cloud-based data lake instantiations on object storage, for example, are all too often modeled as monoliths rather than as distributed architectures. Instead, the future of data integration will move towards a distributed architecture that can run in any cloud or at the edge of the cloud. Borrowing from the service mesh concept of microservices and Kubernetes, this is more of a distributed Kappa speed layer that we call a data mesh. In a conceptual view, the organizing principle for a data mesh are around consumer needs and end users focused working on data domains. These data domains are the driving purpose of a data mesh in the first place. because the scope and boundaries of the domains enable the creation of discrete data products. Data products are the logical collections of data events and historical data that are packaged together to solve some specific business problem. These collections of data may include raw data, prepared data, or more semantically refined canonical data. It is these data products that the business owners care about, and it's the whole reason that IT is funded to provide a data-driven infrastructure in the first place. A modern data infrastructure must be event-centric, and it must be driven by the needs of the data consumer. We can use change events or application events to propagate data anywhere in the world, and stream processing engines can perform data integration in real time in micro batches and even with batch processing. Data will be made available as canonical business objects, as prepared data and flattened views, and also as raw data formats in the structure that the producers prefer them in. There are inherent trade-offs to be made here. For example, the faster that you want data, the less processing can be done on it. Raw data events can happen in a millisecond, but if you want well-prepared data objects in canonical formats, your events may take some additional seconds to fulfill. The good news is that in an event-driven architecture such as this, you will always be orders of magnitude faster than the traditional batch processing models that ETL tools provide. The whole purpose of establishing these three tiers of data semantics is to remain focused on the consumer needs for the data, who may include business users, analytics users, data scientists, data engineers, or DBAs. The whole architecture is designed to be distributed from the ground up. There is no central processing engine and no central hub through which all the processing must be routed, in much the same way that containers and Kubernetes can be used to mesh services across different servers. A data mesh can mesh data across different data stores, regardless of whether they're in a public cloud, a private data center, or at the edge of a 5G network. Once fully realized, data of any shape or format can flow anywhere it is needed instantaneously. The GoldenGate vision for this data mesh is to provide a single pane of glass for development and operations of all aspects of a distributed system. Components may be physically at the edge, but will be managed in a uniform manner. Data will flow as an event-driven basis for both change data capture as well as bulk processing. This is what we call a distributed Kappa architecture. As things stand today, we are substantially into this vision already. We have the core GoldenGate microservices foundation that helps DBAs and data engineers replicate data and events across any global network. And we have a world-class stream processing engine that empowers data analysts and data engineers to create powerful data pipelines, time series analytics, and directly embed production machine learning algorithms into real-time in-memory data streams. Our customers use these capabilities right now to get data into the right formats to the right people at the right moments in time. Some people are already familiar with the GoldenGate brand name, but may not associate it with all these new concepts that we're discussing today. In many ways, GoldenGate has actually been at the cutting edge of these distributed data mesh concepts for a very long time. For example, inside of all transactional databases is an immutable transaction log. Every single activity of the database is recorded. This is what GoldenGate integrates with, so that any database event can be communicated externally in real time. GoldenGate uses its own time-tested protocol called GoldenGate Trail to emit events, and on the receiving side, GoldenGate maintains position information from multiple readers at the same time. Events and data that are transmitted by GoldenGate can be written out to all popular data formats and into hundreds of different combinations of data stores and platforms, all in real time. No batch processing is required. So finally, let's dive into the heart of the topic today and look at how GoldenGate can be used to simplify and improve some common microservice design patterns. One concept to understand right from the start is that GoldenGate is itself a collection of microservices. Back in 2017, the GoldenGate software was fundamentally refactored to be microservices from the ground up. These are fully self-contained C-based microservices with an embedded HTTP service that is used to serve all REST and web-based inputs to GoldenGate. 100% of all GoldenGate features are API-driven via REST. In the microservices community, more broadly, there are many different design patterns. Dozens of books have been written on microservice design patterns, and we are not going to rehash all those patterns here today. Our focus today instead is on the data tier patterns for microservices. These are the patterns that microservice developers may typically employ when designing their services to work with databases, event stores, and other forms of persistent storage. We've already discussed some pros and cons of the database per service pattern, and the rest of our discussion today makes no assumption about whether you choose database isolation or whether you choose to share a database for your microservices. Next up, we're going to talk about how you might use GoldenGate with patterns such as CQRS, event sourcing, transaction outbox, and the Saga patterns. So let's go ahead and jump in. Transaction outbox, in many ways, is the canonical pattern for using replication and change data capture tools with microservices. There's a fair bit that's been written about this pattern, so go ahead and Google it if you really want to go deep into it. In a nutshell, the idea is that you have a microservice that needs to both update data in its local data store, but also notify another service about this update. Ordinarily, the developer might write code for the updates inside the microservice and then wait for a commitment acknowledgement from the database that the commit has happened, and then go through the logic of sending the event to another service or to a broker, for example. But when you implement the transaction outbox, the idea is to simply set things up so that the microservice only has to make a single commit. That commit would go to two tables, the base table and the transaction outbox table. This will guarantee data consistency around using the commit boundaries that the database provides. Using change detection, a replication tool will react to the event placed in the outbox table and replicate that downstream to the service, a broker, or even directly to the receiving service that needs to be notified of the update. The end result by applying this pattern is simpler code in the microservice itself, stronger data consistency, fewer kind of error points where breakage can occur, and you're really delegating the data tier processing to the data tier itself, which seems to make sense at a logical level. GoldenGate in this architecture acts as an exactly once relay for transactions. It's really, really fast and can be extremely flexible in what kinds of payloads the service needs to transmit. Over the years, GoldenGate has accumulated thousands of customers, and there are variations on this outbox pattern which are quite interesting to consider. For example, in the upper right-hand corner, you could remove the middleman, aka the broker, and do point-to-point replication for very low latency use cases that are always single consumer driven, or what I call singletons here. In the lower left, you can skip the step of defining a separate document-based payload and just use the signature of the base tables as your data binding. This is practically a sin for some microservices developers to consider it, but really, what's the difference if your consumers of the data bind to a set of JSON elements that you have to define as your payload versus a collection of columns that are defined in the base table? Data drift and schema changes are challenges no matter which data format you choose. And finally, we've seen some of our customers, often in monoliths or what we may call mini services, they have a desire to set up materialized views where the view becomes the downstream contract for the data bindings, and replication delivers the change events in the format that is specified by the view. The transaction outbox pattern is a very powerful concept that can simplify microservice design patterns elsewhere in the data tier, and it can improve the data consistency for integrated data by delegating events that need to be handled by the data tier to the data tier tooling, such as GoldenGate. What if you could apply this pattern, this transaction outbox pattern, to an enterprise and global scale? What could you do then? This is where the power of the data mesh becomes more self-evident. If every application, microservice, and data store could be continuously emitting events across services into data lakes and being recorded by immutable logs at enterprise scale, then we truly have a mesh of data that can be flexibly reconfigured for any business need on demand and in real time. That's what we've created with GoldenGate. Not only the change data capture and the data replication bits, but also the event messaging, the continuous stream processing for ETL and analytics. More on that later, but let's get back to these microservices patterns. One of the more common and popular microservices patterns is CQRS, or Command Query Responsibility Segregation. Once again, if you'd like a deep dive on CQRS, please Google around for any of the hundreds of explainers on this subject. At a high level, this design pattern is created to segregate and optimize the APIs for reading and writing data in a microservice. The right side APIs are optimized for typical commands that create or update data. The read side is optimized for what might be larger queries that may return larger result sets or data that's been aggregated from multiple services. When used across services, there may be microservices that are dedicated to the read side operations, especially when data from several transaction-based services must be aggregated and queried together as a whole. In this example, on the right side, you have an order history service that contains committed data from orders, logistics, and billing services. The order history provides a common view for the full life cycle. When writing CQRS patterns, developers usually write event handlers to provide service-to-service communications as events occur in real time. By applying GoldenGate and the Transaction Outbox pattern to CQRS, we may remove some of the complexity around event handlers in the application tier of microservices. Instead, we can apply the Outbox pattern to inserts or updates happening on these base services and transmit the events directly to the read-optimized service. As discussed in the Transaction Outbox section, the data bindings could be JSON or tables, and you could decide to use a broker or not. Various pros and cons exist for those decisions. But by using GoldenGate here, you can overcome many of the data consistency issues that are inherited from the decision to leave event propagation to the developer of the individual microservices, relying on event and messaging capabilities of the application tier. GoldenGate is a tool that's been designed from the ground up for high availability, disaster recovery, and high-speed replication. It does a very, very good job of maintaining data consistency and not losing data to the ether. Okay, so perhaps you'll agree with me so far that GoldenGate is going to be a better option for preserving data consistency and reliability, and perhaps even recoverability for the data tier in case of adverse system and network events. I mean, that's what GoldenGate does. It's the DNA of the GoldenGate product. But is GoldenGate actually simpler? Does it help improve the simplicity of these microservice design patterns like CQRS? Consider the case where your consider the case on the left here where your microservice developers write their own CQRS pattern in the scenario above. For each of the three core services, the developers must implement the logic around taking committed transactions and routing them to an event store. The developer of the order history service must implement the subscriber logic to receive the events from the event store and then place them into the aggregate data model of the local data store. If any one of those binding and routing rules fail, the whole CQRS pattern comes tumbling down. In the scenario on the right, using GoldenGate, each developer need only implement the Transaction Outbox pattern for the individual microservices. They can share the use of the same GoldenGate microservice. Since GoldenGate is a microservice itself, it's participating as a first-class member of these microservice event calls anyway. And then the committed and consistent data events that are continuously replicated via GoldenGate can go directly into the order history data store without burdening the developers of the microservices with all that transaction logic. The resulting pattern has less code, fewer points of failure, and actually provides higher service levels around recovery and data consistency. As far as I'm concerned, this is a win-win for microservices developers as well as the users of the applications for the durability and consistency of that data. Event sourcing is a very, very big subject in the microservices community. It's quite common these days to see debates on the merits of Kafka, Akka, or other eventing systems for use as event stores with microservices. However, one of the reasons it's a very big subject is that there are varying opinions about how to use this pattern and how far to go with it. At a baseline minimum, there is consensus that this is a very useful pattern for simple event notifications. For example, if some process is completed and the microservice needs to notify other services, it's clearly useful to use an event store and perhaps also a broker to help with these notifications. But there are others in the microservices community that go further and suggest that the event store could become a replacement for the database, using the immutable log as the persisted store for a record of the events at the microservice tier. Clearly, event stores are not relational databases and all that this implies around data consistency, but for certain kinds of use cases, it is certainly possible to use the event log as a durable store. Furthermore, there are disagreements about whether to leverage shared messages across many microservice implementations. Some in the community have rightly pointed out that if messages are widely shared across lots of different subject domains, the structure of the message becomes the de facto coupling or the binding between services, and in some ways undoes the benefits that microservices are trying to solve for in the first place, which are loose coupling. Essentially, the developers will have shifted the challenges of shared table spaces in monolith databases to shared message formats across monoliths event stores. Finally, it's worth noting that several longtime pundits have effectively said to limit the use of event sourcing to well-scoped domain contexts, so as to avoid system-wide data consistency issues and tight coupling of services. For some, the suggestion is quite simply to avoid using event sourcing altogether in all but the narrowest and most necessary situations. Stepping back to the concept of transaction outbox, it can solve for the most basic of event sourcing use cases quite easily and make it useful at a global system scope. For example, the baseline use case is all about publishing emitted events for simple notifications. The transaction outbox with GoldenGate microservices can simply and elegantly provide application developers the means to publish JSON or table event payloads with very little coding effort and very strong data consistency. For the loosely coupled patterns, it is incumbent upon the event consumer to stay in line with the system schema changes and the eventual and inevitable drift of data shapes over time. For more closely coupled patterns, for example, integration patterns, there must be a contract of sorts that's set up between the producers and the consumers of the data, or at the very least, a predictable and controlled way of managing data drift. For example, when a data format such as Avro is used along with the Kafka registry, there are well-documented patterns to accommodate document schema changes that may happen over time on any given Kafka topic. Event sourcing is a hugely valuable pattern, and one that we would argue is much better off by leveraging the data tier patterns provided by tools like GoldenGate microservices. The Saga pattern has actually been with us since the early days of Corba and the genesis of object-oriented integration patterns. Essentially, when different software components must work together to complete a transaction, they must have some type of choreography or orchestration logic, and they must also have a means to undo discrete transactions if the larger Saga fails. Back in the days of service-oriented architectures, the Saga pattern was systematically taken care of by the frameworks that provided business process management and event broker capabilities. But in the microservices community, this pattern has emerged again, largely due to the prevalence of the one database per service dogma. Without a shared database or a common top-level broker, it's up to the microservice developers to ensure that the long-running and multi-step transactions can complete, and that when they fail, that they fail gracefully. Although not as prevalent as other patterns that we've discussed thus far, it is interesting to note that others have already experimented with using the transaction outbox pattern for sagas. In this scenario, the coordinating services use the outbox plus a tool like GoldenGate to post messages into a shared event hub. As the multi-phase transactions complete, the coordinating services are listening for events from the other services participating in the saga that may precede them. If any of the coordinating services fail, the event notification would be consumed by all services and the necessary rollbacks or compensating transactions would be issued. Introducing the outbox pattern into Saga would improve the reliability of the data events and decrease the complexity for what must be coded in the individual services. Since GoldenGate is itself a microservice, it could simply be a participant in the overall choreography of the systems. A passionate topic for many inside the microservices community is around aggregates. Aggregates are a collection of data objects that are grouped together by a particular microservice. Within a small and well-defined scope, such as a domain context, the aggregate is mainly a convenient way to work with collections of data elements at once. However, some microservices developers may use aggregates to send data to other services. In this case, the aggregate becomes a payload intended as an integration event for others to consume. For these integration events, the transaction outbox is once again an ideal solution for the problem. Individual services may construct an aggregate of their own definition and then place it within the outbox for a tool like GoldenGate Microservices to replicate to another event broker, or directly to the consuming service that may use the aggregate directly. Once again, the GoldenGate microservice becomes the enabling technology to simplify and enable this core pattern to provide higher levels of data consistency. In fact, now that we're talking about integration events, it's worth pointing out and reminding the audience that integration is exactly the heritage of GoldenGate software itself. GoldenGate began as a provider of integration events for databases, covering multi-active, fan-out, fan-in, and many other patterns for database event replication. More recently, GoldenGate has become widely used for integration events with non-relational systems, such as data lakes, big data streaming platforms, and all major public clouds for NoSQL or SaaS applications. Now, most recently, what we see in the broader GoldenGate platform is it being used for integration events for data pipelines, continuous ETL, time series analytics, and machine learning-based predictive analytics. So I hope it's clear by now that not only can GoldenGate microservices help to simplify and improve data consistency of many app dev design patterns, but it can also provide the backbone for data mesh-based integration events as well. All right, so now that we've introduced the idea of the data mesh and that we've explained how GoldenGate can help improve core microservice design patterns for data, I wonder how many people listening in today remember what complex event processing tools are. Dating all the way back to the 1990s and achieving some levels of market hype by 2009, the complex event processing, or CEP space, was really quite the hot topic in enterprise software for a moment in time. I like to joke that any software product category with the word complex in its name was probably doomed to fail. I don't know who coined this term, so no offense intended if you're listening. In some ways, CEP was just too far ahead of its time. The sophistication, infrastructure requirements, and proprietary frameworks were too much of a hurdle for widespread adoption. But interestingly, now with the emergence of several open source big data streaming frameworks, we're seeing a new springtime for CEP-like use cases for event processing. The open source stream processing frameworks that have recently emerged, such as Apache Storm, Apache Flink, Apache Spark Streaming, Confluent KSQL, are not exactly as sophisticated as the classical CEP engines, but they have the benefit of being free and being built for massively parallel processing runtimes. As these frameworks are maturing, they're starting to take on more and more of the conventional CEP type expressiveness. Conversely, the classical CEP tools, which by the way still serve a sizable niche in the enterprise software market, are increasingly making moves to adopt more of the open source friendly frameworks such as Apache Beam and Apache Spark. For many complicated IoT and telemetry use cases, CEP tools are still the far superior choice for providing rich and mature feature sets. Finally, it's worth mentioning that there exists a third important category around time series databases, which specialize in temporal queries and very fast write and scan times for telemetry type data. In fact, some newer stream processing entrants, such as Kafka KSQL, are actually building their entire stream processing engines on top of key value data stores like RocksDB. The surge of interest these days is neatly summed up by Roy Schulte of Gartner, who notes that the widespread awakening around event-driven architectures has been picking up lately. You see, once we've gone down the path of a service mesh and a data mesh, you have all these events happening and you need to do something with those events. You want to do something with those events to help the business use case. Stream processing and CEP answers this question. And the solution is to make use of a processing engine that can work on events as they arrive, one event at a time, or with groups of events that are happening within time windows. As you begin to see the world of data as events, it becomes obvious that batch processing is just a collection of data events grouped together by time. Given enough scale and power, you don't need separate engines for batch processing. A good stream processing engine can cover your low latency, high volume, and batch processing pipelines in a far simpler architecture. Practical use cases such as continuous ETL event pipelines, time series analytics, geospatial analysis, and real-time scoring for machine learning models can all happen in these same kinds of real-time pipelines as part of this data mesh. GoldenGate Stream Analytics is Oracle's spotlight technology in this area. This platform is an integral part of our data mesh vision, and it can be used to visually construct data pipelines that perform continuous ETL or advanced analytics on any data that is moving in real-time time windows as small as 1 millisecond. With this tool, you can easily ingest data events from all databases using GoldenGate. You can use source connectors from Apache Kafka Connect to connect to an additional 100 plus or 150 plus sources. You can also use JMS, MQ, or AQ technologies to send events into stream analytics pipelines as well. This tool makes it easy for developers to create data pipelines and deliver data back out to data stores such as object stores, data warehouses, or even back to external messaging systems such as Kafka. The GoldenGate Stream Analytics tooling began its heritage as a world-class CEP engine that had been top-ranked by a number of analysts who previously covered the CEP market space. The IP is time-tested and proven. It runs on a core engine for hosting what is called CQL, or the Continuous Query Language. Approximately 3 years ago, we at Oracle determined that the open source frameworks offered a superior hosting platform for the core CEP engine. So what we did is we took the core engine and we refactored it to run on top of a runtime consisting of Apache Kafka and Apache Spark. The core IP of the CEP engine is still intact, and CQL is still the base language for expressing stream semantics. But now our customers can host, scale, and manage the platform on widely available Apache frameworks that run in the Oracle Cloud, non-Oracle clouds, and within environments that many Global 5000 companies are already running in-house. Unlike the open source streaming tools, this GoldenGate Stream Analytics tool is a low-code environment. Developers may graphically construct data pipelines in an interactive manner. It's easy to select from predefined patterns to accelerate key analytics for time series, geospatial, and embedded machine learning. Since it is low-code, the tool may also be used by data analysts directly to build and embed real-time dashboards that are event-driven. These are not SQL dashboards that need to be refreshed. These dashboards run continuously and have events being pushed to them in real time. There's definitely a lot going on in this chart, but we've included it here to really give you a flavor of what it is like to use the graphical language of this tool. GoldenGate Stream Analytics is not just another pretty face. We don't have time today to go into a deep dive comparison of streaming platforms, but I'll briefly point out that since the heritage and DNA of this GoldenGate stream processing tool comes from a CEP background, the richness of the processing semantics and windowing functions are on par with the best CEP engines in the market, which are generally considered superior than the more basic capabilities emerging from the open source community in the past few years. Also, as a key focus of development for this tool has been around ease of use and providing analytic capabilities. Neither of these points are seriously addressed by any of the mainstream open source stream processing tools. And finally, perhaps most importantly in the context of today's subject, I wanted to point out that since this is a GoldenGate tool, the use cases we target are subject to very strong data consistency semantics that are typical for enterprise databases. We've invested in this streaming platform to ensure that exactly what semantics are adhered to, that record by record processing is possible in the correct order, and that's part of the standard deployment model. We've invested in patterns for handling inserts, updates, and deletes on complex business objects, and that the event streams themselves are aware of transaction commit boundaries from source databases. Our goal for this platform is for industrial strength and mission critical enterprise systems. Okay, so finally, good time to step back and wrap up this discussion today. I hope that I've been able to communicate our strategy and approach around the data mesh. Microservices are a foundational aspect of GoldenGate itself, and the GoldenGate microservices can also be used to simplify and improve the design patterns that application developers are using to create their own microservice-based applications. As we push forward in time, we believe that forward-thinking IT organizations will prioritize these event-driven architectures, that they will take a consumer-oriented view on organizing data subject areas, and that the power of distributed software architectures will empower a new generation of data mesh characteristics for enterprise data assets. As a concluding thought, the ideas that we've discussed today are not incremental in nature. These are not incremental improvements on data architectures of the past. We're contemplating a sea change here. This kind of change in thinking requires a new level of analysis. To think of the universe of data as something that is dynamic, constantly changing, event-driven, is the antithesis of the old ways that imagine data as some kind of static asset that resides in a database or on a hard drive. Once the mindset shifts to accept data as dynamic, constantly changing events, the way you will approach modeling, mapping, pipeline development, and data governance must also change. What we've been discussing today is not a metamorphosis. It's a paradigm shift in thinking around data management architectures. Well, that's it for now. Thanks for listening. Really appreciate your time during these crazy times that we live in today. I will go ahead and pause now for some questions, just to take a look at what's come in on the Q&A.